Hello everyone, welcome to Unit 2. In this unit we're going to take a look at the basics of GPS and its accuracies and the systems that kind of tie in with that. Reason why we start with this is you look at a lot of today's modern precision ag equipment, a lot of it needs that GPS in order to record the data, to record the information. So this is kind of one of the vital units, and having a basic understanding of GPS to begin with makes a whole lot more sense and makes it a lot easier as we go through the rest of the course. So with that, we'll go ahead and begin. As usual, we're going to begin with a little bit of history. So most of you probably realize by now the GPS system basically works off of satellites that are up in the sky. So kind of the way that began was in 1989, the Department of Defense, the U.S. government's Defense Department, launched the first production series of GPS satellites. They had started doing some testing prior to that and looking at GPS and how it could work, and saw benefits of that. So that is what led to launching it in 1989. And within 4 years, there was a full constellation of 24 satellites. And you're going to see where this 24 comes into play here in a little bit. But in December 8th of 1993, just a mere 4 years later, it was declared fully operational. And right now, if you take a look at the Department of Defense, there is currently about 28, roughly give or take, GPS satellites orbiting the Earth. Some of the original satellites are no longer working, so they've gone out of. They're no longer active, so they're constantly being monitored, and they're also being replaced. So yeah, right now, typically 27, 28, 29 satellites are up there orbiting the Earth, and what the goal is, and you're going to see where this number 4 comes into play here in a little bit, but the goal is that we want to have at least 4 satellites visible at all times. So no matter where I'm standing on the face of this Earth, I should have 4 satellites in visible range. Doesn't matter where I'm at, and this is at any time, at any given time. So that is kind of what their ultimate goal is, and that's is key for it to work. So to kind of put it into reference where these satellites are at, we'll kind of take a look and just kind of give you some perspective. So here's good old Mother Earth. And basically the circumference, if we were to measure it anywhere around the Earth, whether it's from the North Pole around through the South Pole back to the North Pole or around the equator, we're roughly 24,000 miles. And if you think about it, we have 24 hours in a day. So at the widest circumference around the equator, each time zone is about 1,000 miles wide. As it gets closer to the poles, it kind of narrows up a little bit. So that's the circumference. In terms of rotation, just by us standing here, the Earth is rotating at about 1,000 miles an hour around the sun. And that's what kind of gives us our one-day cycle. So circling around the Earth, or circling around the sun, we're moving about 1,000 miles an hour, and that completes our 24-hour cycle. So that's the size of the Earth. So here we'll take another example. So here's the International Space Station that is currently orbiting over the Earth. Its current distance from the Earth, if we were to straight up into the sky, it sits at about 230 miles straight up, and that's where it orbits at. So kind of put that, 230 miles. Think about what is 230 miles away from your location. For me, that is going up from here in Iowa Falls. That is going up into middle of Minnesota, all the way down to Kansas City. That's how far up the space station is from the Earth's surface. So the GPS satellites, and there's a reference picture of one, what it looks like. And to kind of give you some perspective on that, the size of these satellites typically are no bigger than the size of a classroom, maybe 20, 25, 30 feet widest at the most, including the panels. So you see the solar panels there, that's what powers them. They get the solar radiation, that's what keeps them powered and keep them active. So what is their distance from the Earth? Well, their distance is, to put this in perspective, like we said, the International Space Station sits at 230 miles up. These sit at about 11,000 nautical miles. Now, most of you probably don't know what a nautical mile is, so I'll make it easy for you. That is in statute miles, that is roughly 12,600 statute miles. So those satellites set up there quite a ways further up. And they're actually orbiting around us. And so in a typical 24-hour period, they'll make 2 rotations around the Earth. And roughly they're traveling at about 7,000 miles per hour. So, the question is, why are those satellites up so high? And this kind of gives you kind of a reference for that. So down there at the bottom we have Mother Earth. Imagine if I had like the International Space Station sitting up there where my satellite was at, where the International Space Station is at 230 miles. At 230 miles, it's not going to see as much surface of the Earth as something that's sitting 11,000 miles up. So the higher up we go, the fewer satellites we're going to need, because those satellites can cover a bigger portion of the Earth's surface. So the reason why they sit so high, so we can get that coverage across the Earth and do it with the minimum number of satellites. So the satellites themselves, kind of give you a reference here. They're actually, when they rotate around the Earth, they're rotating on 6 different planes. If you took a look at this image, you can kind of see there's an image where the satellites kind of rotate around the equator. That's one orbital plane. There's another one that's kind of going at an angle here. And then the other 4 planes are basically kind of on a north to south type track. So that is the 6 different planes that they orbit on. So it's not just randomly floating through the sky. They're actually rotating on those axes, if you want to call it that. And so here is kind of a reference image for you. As you can kind of watch this animation, pick this off the internet several years ago. So we can kind of see the Earth. There's the Earth rotating there in the center. On that Earth, there's someone standing there with a GPS receiver. So as the Earth is rotating, the satellites are also rotating in their own orbital planes. And as the satellites are rotating, you can kind of see the black dotted satellites. Those are the ones that the person standing on the Earth can pick up. And you'll notice some of those, they'll be black for a little bit and they turn red, because now all of a sudden they're going to orbit out of range to where we can pick them up on the face of the Earth. So as we're rotating around, so are the satellites rotating around on those 6 different orbital planes. So far so good? Great, we'll keep moving on. So what kind of makes these work, or how can we start determining our position with these satellites? Well, what makes it happen is that these satellites have an atomic clock built into them. And these clocks are the most accurate clocks that we're ever going to find. And they're really, really, really pricey. The other thing is that these clocks and the satellites are monitored, and they're constantly being adjusted by the Department of Defense. You'll see where this adjustment thing comes in a little bit. But just to kind of give you some accuracy, they're accurate to within very few nanoseconds, as in 10 to the minus 9th seconds. So that would be 0.000000001. So that is how accurate they are. Now, if they're off by 1 millisecond, as in they're off by 0.001 milliseconds. So if they're off by just that amount, that could put our position on the face of the Earth somewhere within a 186 mile range of where we are to where it says we think we are. So to kind of give you a reference of what 1 millisecond is, and I'll kind of give a reference to what 186 miles is, when you blink your eye, probably some of you are going to do it right now just to test it. When you blink your eye, that takes 300 to 400 milliseconds. So what we're talking about here is something that is in 1/300th to 1/400th of the time it takes you to blink your eye. My GPS satellite, if it's off by just that little bit, is going to put me off by 186 miles. So since I'm here in Iowa Falls, what is 186 miles for me? I actually used a little bit of GIS software a while back, and I mapped this out. So I went in and said, okay, here's Iowa Falls, give me a 186 mile radius. That's what that radius is. So if my GPS is off by 1 nanosecond, we said, it's going to put me off somewhere in that range. So if I think, if my GPS says I should be in Iowa Falls, but if my GPS satellite's off by 1 nanosecond, it's going to put me somewhere inside that circle. which I could be anywhere in the state of Iowa, as well as I could be all the way up towards Minneapolis, St. Paul, or down into northern Missouri, or out into the western parts of Illinois. So it's amazing just how you're off by a little bit and what effect that will have. So start breaking it down. How does it work? So what happens is our satellites up there, they're actually transmitting out a radio signal. That radio signal is what's called a pseudo-random code, and that basically means it's supposed to be random, but it really isn't. There's actually, some rhyme and reason to that. And so when that signal gets beamed out, it says I beamed out exactly at this time period using that exact clock. My GPS receiver there on the ground is going to pick up that signal, and it says this is the exact time that it hit me. And what it does is it calculates out a time difference. And it says it took X amount of time to get from the satellite to the receiver. So, a little bit of basic science for you is we're trying to calculate the distance. So distance is a calculation. We're going to take the speed, and we're going to take that times the time. Well, we just calculated out what the time how long it took for the time to get from the satellite to the receiver. So we know that time factor. And the basic rule is if we know two of the factors, we can solve for the third. Well, we know the time. The speed is a given. The speed is going to be the speed of light. That signal is transmitted at the speed of light. And just for a reference, speed of light is rated at 186,000 miles per second. Now, in terms of miles per hour, we're talking about 671 miles an hour. So, if we know the speed of light at 186 miles per second, we have the time, we can then calculate the distance. And what we're doing is we're calculating the distance from the satellite. So how far is our receiver from that satellite? And it's going to put it into reference of feet or miles. Okay, so if I have one satellite, if I'm just picking up one satellite, and we're talking about in a three-dimensional world here. So let's say my GPS receiver says I picked up one satellite signal and I am 11,000 miles away from this satellite. I could be 11,000 miles in any direction from that satellite. So think of a sphere. That sphere is 11,000 miles around. So my position could be anywhere on the surface of that sphere. So just picking up one satellite is not going to give us a very precise location. So we'll add the equation up a little bit. We'll throw in, what if I'm picking up two satellite signals? So here I have two satellites. I'm picking up that signal from both of them. So now where we take those two spheres and where those two spheres connect together, where they come together, it's going to basically be, we can be along any position along a circular intersection where those two spheres come together. So as you can kind of see in the image here, my round circle over here is basically where those two spheres come together. So, still not very precise because I could be anywhere on that circle. Well, now if I add in a third satellite, wherever those three spheres come together, wherever they intersect, that's going to take that one where with just two I had a ring. Now I've narrowed it down to just two possible positions on that ring. So what's going to happen is one of those positions is going to be on the Earth. The other one is going to be up in space. So then what happens, how I can get my GPS location is when I add in a fourth satellite. That fourth satellite is going to eliminate, is it this X or is it this X? So for a GPS satellite receiver to work, we need to be picking up a signal from at least 4 satellites. Any less than that, it's not going to work. Okay, we finished the first part of this unit, so we're going to go ahead and pause it right there, and we'll pick up with the next video series here shortly.